Hello everyone, welcome to session number 23 of Java programming. In today's lecture, we are going to study thread synchronization techniques and inter-thread communication. This topic is extremely important because multi-threading improves performance, but without proper control. It can also create serious problems in real-world applications. In the previous lecture, we learned how to create threads in Java. We discussed two approaches, creating threads using the runnable interface and creating threads by extending the thread class. We also understood why implementing runnable is generally preferred in professional Java applications. Let us understand today's topic with a real life scenario. Imagine two threads, one representing an ATM withdrawal and another representing a UPI transaction. Both are trying to withdraw money from the same bank account at the same time. If synchronization is not used, both threads may read the same balance and withdraw money incorrectly. This can result in an incorrect final balance. So the question is, how do we ensure that only one withdrawal happens at a time? The answer is thread synchronization. At the end of this session, you will be able to understand why synchronization is required in multi-threading, and you will be able to explain and apply different synchronization techniques and inter-thread communication mechanisms in Java. In this session, we will first understand the need for synchronization, then we will study different synchronization techniques, followed by inter-thread communication methods, examples, activities, and a summary. Thread synchronization ensures that shared resources are accessed safely by multiple threads. It prevents data inconsistency and race conditions. Inter-thread communication allows multiple threads to cooperate and share information effectively, instead of running independently without coordination. When multiple threads try to modify the same shared data simultaneously, race conditions may occur. Without synchronization, proper output becomes unpredictable. Synchronization ensures data integrity, consistent program behavior, and controlled access to shared resources, which is essential in concurrent applications. Java provides multiple synchronization techniques. These include synchronized methods, synchronized blocks, static synchronization, logs such as reentrant logs, semaphores, and monitors. Each technique has its own use case and level of control. A synchronized method is used to lock an object for any shared resource. Only one thread can access a synchronized method at a time. For example, if an increment method is synchronized, only one thread can execute it at a time. This prevents race conditions when multiple threads try to update the same variable. Synchronized blocks provide finer control over synchronization. Instead of synchronizing the entire method, only the critical section of code is synchronized. The syntax uses the synchronize keyword with an object. This approach improves performance by limiting the scope of synchronization. Locks such as reentrant lock provide explicit locking and unlocking mechanisms. They offer more flexibility compared to synchronized methods. Semaphores control access to a resource by multiple threads. They are essentially useful when we want to limit the number of threads accessing a resource simultaneously. Every Java object has an implicit monitor associated with it. This monitor is used automatically by synchronized methods and synchronized blocks. Monitors ensure mutual exclusion and proper coordination between threads without requiring explicit handling by the programmer. Inter-thread communication allows threads to communicate with each other using the wait, notify, and notify all methods. This helps avoid busy waiting and improves CPU utilization. The wait method causes a thread to wait, notify wakes up one waiting thread, and notify all wakes up all waiting threads. When a thread calls wait, it releases the lock and enters the waiting state until it is notified. Notify wakes up one waiting thread, usually used when only one thread needs to proceed. Notify all wakes up all waiting threads and is useful when multiple threads are waiting on the same object. In this example, we have a chat class with a Boolean flag. The question and answer methods are synchronized. The wait and notify methods are used to ensure proper coordination so that questions and answers are executed alternately in the correct order. The output of this program shows that the answer is shows that the question is printed first, followed by the answer. This confirms that inter-thread communication is working correctly and the threads are properly coordinated. In this activity, students demonstrate race conditions and synchronization. Without rules, multiple students updating a shared resource create confusion. When a lock is introduced, only one student can update the resource at a time. This clearly demonstrates the importance of synchronization. Synchronization prevents data inconsistency and ensures thread safety. It facilitates proper coordination among threads and improves the reliability of concurrent and multi-threaded applications. Despite its advantages, synchronization has challenges. It can lead to deadlocks due to circular weights, reduced performance because of blocking and debugging. Multi-threaded programs become more complex. The wait method pauses the execution of a thread and releases the lock. Notify wakes up one waiting thread. Notify all wakes up all waiting threads. Choosing the correct method depends on how many threads need to be resumed. Different synchronization techniques offer different levels of control and performance. Synchronized methods are simple, synchronized blocks are efficient, locks provide flexibility, and semaphores control concurrent access. Selecting the right technique is crucial for optimal performance. To summarize, synchronization ensures safe access to shared data in multi-threading. We studied synchronized methods, blocks, logs, semaphores, and monitors. We also learned how inter-thread communication enables threads to cooperate effectively. These concepts are essential for building reliable and thread-safe Java applications. In the next session, we will study multi-threading case studies and apply these concepts to real-world programming scenarios. Now we'll be solving a case-based scenario problem. As you can see, a banking application has multiple threads performing deposit and withdrawal operations on a shared account object. We have to solve these three subparts A, B, and C. In the A part, design a Java program that ensures thread safe access using appropriate synchronization techniques. Then we'll be solving B and C part. As usual, we'll be using IntelliJ IDE for writing this program. So as you can see, we have named the project as Inter-Thread Communication. As usual, you can create this object using the file menu. Then you go to the new menu item and then new project. Give the name of the project and then create. And let me hide the folder structure so that entire screen becomes visible to you. So line number one is class bank account private int balance. So bank account is the shared resource. Balance is a critical shared variable. It is marked private to protect data integrity. Then line number four, public bank account int initial balance. This dot balance equal to initial balance. So this code initializes the account with an initial balance. This dot balance refers to the instance variable. Then we come to line number nine, public synchronized void deposit int amount. Synchronize keyword ensures only one thread can execute this method at a time. The object lock of bank account is acquired. Then we come to line number 10. Balance plus equal to amount. It safely updates shared data. No other thread can modify balance simultaneously. Line number 11. System.out.println thread.current thread.getName deposited plus amount plus balance. So this code displays thread name. It also displays deposit amount. It also displays updated balance. Then we are calling the notify all method in the line number 13. So this notify all method wakes up all waiting threads, especially important for withdrawal threads and waiting due to its insufficient balance. It prevents starvation. Then we come to line number 17. Public synchronize void withdraw int amount. Here the synchronize keyword ensures mutual exclusion. Only one thread can attempt withdrawal at a time. Then we come to while loop in line number 18. While balance is less than amount, This statement uses while loop instead of the if statement. It handles spurious wake ups. It rechecks condition after every notification. Then we come to line number 19, system.out.println thread.current thread.getName waiting due to insufficient balance. So this statement informs that withdrawal cannot proceed. Then we are having a try block, line number 21. Wait method is called. Here the thread releases the lock. Thread enters waiting state. It also allows deposit thread to acquire the lock. It prevents CPU waste, that is, there is no busy waiting. Then we are having line number 23, catch block interrupted exception ee.print stack trace. So this code is mandatory exception handling. It handles unexpected thread interruption. Then we come to line number 27, balance minus equal to amount. This statement executes only when balance is sufficient. Save deduction due to synchronization. Then system.out.println thread.current thread.getName withdraw plus amount balance plus, that is line number 28. It prints withdrawal details and remaining balance. Then we are having the line number 33, class customer extends thread. This represents a bank customer. It extends thread to perform concurrent actions. Then we are having line number 34, private bank account, private boolean is deposit, private int amount. Here the account is a shared bank account object. Each deposit determines the operation type and the amount is the transaction amount. Then we come to the line number 38. Public customer bank account comma boolean is deposit comma int amount. This statement initializes shared account, initializes the operation type, initializes the transaction amount. Then we are having the run method in the line number 44. Public void run, it is the entry point for thread execution. Then we are having the if statement, if is deposit account dot deposit amount, else account dot withdraw amount. So these statements mean if is deposit is true, then deposit operation will be carried out, otherwise the withdrawal operation. Both operate both operate on the same shared account. Then we are having the main class because main method resides within this class in line number 52. This main class is a driver class and it contains the main method. Next, we are having line number 54. Bank account is equal to new bank account. We pass 500 as a parameter. So this statement creates shared account with an initial balance of rupees 500. Then line number 56 and 57. New customer, line number 57. New customer account comma false comma 800 dot start. So it represents a withdrawal thread. It attempts to withdraw rupees 800 and it goes into the waiting state due to insufficient balance. So like these were the line number 56. Then line number 57. New customer account comma true comma 1000 dot start. So it is represents a deposit thread. It deposits rupees 1000. It calls notify all method. Wakes up withdrawal thread. So summary of this program is withdrawal thread starts first. Balance is insufficient. That is, it will lead to thread. That is, thread calls the wait method. Deposit thread executes and adds money. Notify all method wakes up waiting threads. Withdrawal resumes and completes safely. Why this program is thread safe? Because the synchronized keyword ensures mutual exclusion. Only one thread accesses balance at a time. While loop prevents spurious wake-ups. Wait method releases lock safely, and the notify all method wakes all waiting threads. Then we can run this program to see the output. Build process starts. As you can see, the output is it. This is the output of the program, as you can see. Now we'll be solving a case-based scenario problem, that is B part. A part we have already answered. In B part, that is evaluation of wait, notify, and notify all methods for insufficient balance. So why the wait method is required? Wait method is required when the balance is insufficient. Withdrawal must pause. Busy waiting wastes CPU. Wait method releases object log. So the concept is puts thread into waiting state, resumes only when notified. So why notify all method is better than notify method? If only notify method is used, a deposit may wake another deposit thread. Withdrawal threads may starve. Notify all method ensures correct thread selection. So now we'll be solving the C part, that is critically analyze the risk of deadlock and starvation in synchronized multi-threaded applications. So first question is, what is deadlock? Deadlock is a situation where threads wait forever. Each thread holds a resource needed by another. Example scenario of deadlock can be, for example, a thread locks account 1, so it waits for account 2. Thread B locks account 2 and it waits for account 1. Why deadlock happens? Deadlock happens because of nested synchronized blocks, because of circular dependency, because of improper lock ordering. What are the prevention techniques to prevent the deadlock? First, you have to maintain the consistent lock order. Now, next is starvation. What is starvation? Starvation happens when a thread waits indefinitely. Other threads keep acquiring the lock. What are the causes of starvation? Excessive use of notify method is one of the cause of starvation. Then thread priority misuse or long running synchronized blocks is also the cause of starvation. Then mitigation strategies, how to reduce the starvation. You have to prefer always notify all method. You have to use the fair logs. You have to use the re-entrant log as well. So the conclusion is synchronization ensures correctness but introduces complexity. Wait and notify all methods are ideal for banking scenarios. Poor design can cause deadlock or starvation. Efficient locking strategies are critical in real world systems. So we have solved the case-based scenario problem. So thank you for watching this lecture. If you found this video useful, please like, share and subscribe to the channel. See you in the next session.